Howdy folks, long time no see. For over half a decade now, I have been researching and studying neutron stars. I started as a student in university, and I continue to this day even after getting my degree, which you can see back there, in physics. And I'm absolutely obsessed with neutron stars, for those that don't know. Some of you could have probably figured out by now that I do research neutron stars with some of the videos I've made with regard to HESOFT, HESARC, and nicer data analysis and stuff like that. But I've never really come and explicitly talked about neutron stars, which I'm absolutely obsessed with them. And after talking to a number of people, they said, you know, Nick, you can really pretty much chew anyone's ear off when it comes to the topic of neutron stars just because I'm so damn obsessed with them. Basically asked me, why haven't you discussed it more on the internet? And, I don't really know why. I've always wanted to, but for whatever reason, I just haven't, and that's going to change today. And I figured the best place to start off talking about neutron stars, neutron star physics, astronomy, astrophysics, all that stuff, is with a theorem, or at least a phrase, that most references attribute to David Pines, and that theorem says, neutron stars are superstars. And that doesn't necessarily mean that, neutron stars are so super, thumbs up, awesome. No, that's not the case at all. David Pine said this because of the super exposure you will get to all different areas of physics with regard to studying neutron stars, and also with the super extreme physics that you will get to experience. But you see, after doing research and studying neutron stars and doing all different things with regard to neutron stars, I've realized that that's not really a full theorem if you're just going to talk about the physics. Really, neutron stars are superstars because of the super exposure to all different areas of STEM and also some of the extreme areas of STEM that you will encounter when studying neutron stars. Now, to really best understand the Pines theorem and why it resonates with me so much is because when I was a student, like any student, you have to choose something to research. And I was looking at all the different research labs and all the research opportunities I had at my university and even at other universities. And so much of it was really, really interesting to me. And I realized I pretty much couldn't study it all. I knew I kind of liked astrophysics, and so I wanted to do something in astrophysics anyway. But so many of the other labs, like quantum physics, photonics, and all these different things, even stuff in material science, was really fascinating to me. And I wanted to get exposure to all these different things. And when I was reading up a lot on neutron stars, I realized, hey, pretty much every single area of physics is being touched in a significant way when studying neutron stars. You have your quantum stuff, you have your classical stuff, you have, your non-Newtonian relativistic stuff, of course, because, we're dealing with ultra-dense balls of matter. And there's so many super qualities that are with superstars like a neutron star that basically give credence to this theorem that neutron stars are superstars. And the super extreme physics is also what really interested me, and that's why ultimately I started studying neutron stars. To kind of give a few examples of how neutron stars are touching on every single area of physics, you kind of need to look no further than the equation of state as the first place to stop off at. I mean, you have basically an ultra-dense ball of matter. So you have condensed matter physics, solid-state physics, your QED, QCD, all the really interesting and awesome stuff that goes on with that. And, of course, it's a big, it's a star. So all the nuclear physicists, of course, are getting in there because anytime you have a star, well, nuclear physics is having its place. There's so much exposure to all of that, different types of modern physics, but then you go on the opposite end with regard to equation of state, that kind of takes care of the thermonuclear side of stuff with regard to the thermonuclear pressure that's going to be holding this star up. And then you obviously need to factor in what's going to counteract that thermonuclear pressure, because the star is, it's there, it's basic. I don't want to say you could draw a free body diagram for it, but that's the way that I like to think about it, where you have thermonuclear pressure out, you need gravity coming in, and, you have about 1.4 solar masses of matter packed into a sphere that is 15 kilometers in radius. So this is ultra dense. So you need to have a good understanding of your general relativity and how that plays into all of this. And that makes this really, really interesting. And, it's not just that. Even take something like magnetars, for example, which, I study a few of them, but I'm not super well versed in the magnetar stuff. I'm studying them for many other reasons. Magnetars are basically where we see some of the strongest magnetic fields in our universe, and that makes the behavior of magnetars and neutron stars really, really interesting. So you're dealing even with extremes of not what I would say was like modern physics, but even electrodynamics and things like that, whether you're doing it in a classical sense or a quantum sense. Even with regard to just like basic classical mechanics, there was a situation where I basically had to ask myself, hey, how fast can a pulsar spin before it rips itself apart? And I just did a very, very simple classical mechanics approximation. You basically are just doing a very simple classical mechanics problem. So you're even getting to some extremes with just basic classical mechanics. You're getting so much exposure to all the different areas of physics with regard to what neutron stars offer, or what you'll encounter when you start studying neutron stars, but you're taking all of that to the extremes, and that's why neutron stars are superstars. You're getting a super amount of exposure to almost every single area of physics, and then you're taking that to the extremes and actually making it super. And it's not just really the physics, too, that you need to think about with regard to this. Like I said, it's super STEM at this point. I started off doing theoretical astrophysics for this. I thought I was going to be doing the more stuff on the theoretical side of things. But what I ended up doing, and what I've pretty much been doing for most of the time, is actually much more within the realm of astronomy, not so much astrophysics, but more on the observational side of stuff. And when you ask any astronomer or astrophysicist at this point that does observing work, they're pretty much going to tell you that a lot of modern day observational astronomy is just coding and data science. You not only need to be super well versed in the physics that's going on with this, and even be kind of comfortable taking some of that physics to the extremes, but you also need to be pretty well versed in how to work with the technology you have at your disposal, and also with regard to like software or data engineering. And then a lot of that involves actually dipping into some of the mathematics and stuff like that, especially if you want to talk about things like machine learning and whatever else. That's why I've been doing a lot of the videos that I've been doing on linear algebra, because linear algebra, I've noticed, plays a really important part in almost everything I do. Actually, for a day job, I write code, so it makes sense there. But I'm using linear algebra all the time, and so it's really important for me, at least, to kind of dip into that again like before. And so for those of you who watch my videos more so for the mathematics type stuff, that's not going to go anywhere. As a matter of fact, I think one of the best ways of learning and better shaping things up is actually by teaching. That's a discussion for another time. But David Pines was really, really correct when he said this phrase. At least I was not there. I was not even alive when it was referenced that David Pines said neutron stars are superstars. But David Pines was a very, very smart man, and he was very correct in saying neutron stars are superstars, not just because of the super exposure to such a wide range of all the different areas of physics, but not just because of the super extremes of physics, but also because you really need to have a good level of understanding with regard to everything in STEM with that. With your science, obviously you've got your astronomy, astrophysics, and physics in there. Which to touch on the astronomy for a moment, you need to be willing, or at least somewhat knowledgeable in how astronomy works in almost every single band, especially if you're studying pulsars, particularly like I am. Like I just said, I particularly study pulsars, and I mainly do that at the higher energies, particularly X-ray, but I do dip into gamma ray, so I need to know the differences between X-ray astronomy and gamma ray astronomy. But then it's also pretty useful sometimes to dip into optical, or when you're talking about pulsars, you can't really talk about pulsars without talking about radio, because pulsars, or at least their spins and stuff like that, are measured with radio data. And so you really need to have a good understanding of how astronomy works in almost every single different band and all the different weird oddities and differences that go on with that. And of course, if you're doing, like I said, observing work, you're going to need to understand how to program. Python is pretty good for that nowadays, but you can look back and you can look at some like the HESOFT source code, at least for some of the nicer packages and whatever else. That's also all in Perl. The like CFITS.io is written with C. So understanding programming and computer science or even data science, data engineering with stuff like that is also really important, especially when now you start having people who are taking machine learning or AI type technologies and applying that to their work in astronomy and astrophysics. It's incredible. You need to have a really good understanding of all that. And it's not just a software engineering thing that you need to better understand. It's also a physical hardware engineering type of thing. One of the things that I don't want to say famously did wrong, but people who were around at the time, and judging by the fact of the number of emails that I got, when this all happened, the first paper I tried to publish, I got numerous emails saying, hey, your result is wrong because you did not factor into, this particular problem with regard to doing timing analysis with the NuSTAR mission. And that's very much a hardware as much as it is a software problem. So you need to have a good understanding also about how the hardware works. I mean, you don't need to be an expert in it, of course. I'm not going to say I'm an expert in how to actually, like how to build a mission like NICER or XTE or NuSTAR or anything like that. But you need to at least have a basic understanding of how it was kind of constructed and what some of the limitations are with regard to the hardware. And so you need to not just have a software understanding with regard to some of the stuff with studying neutron stars. You need to have a hardware understanding of some of the tools that are gathering the data that you're using for your analysis. And all of that, again, is tied together with a lot of the mathematics, especially when you start talking about AI, machine learning, and that type of stuff. But, of course, with all the physics, this is what is holding it all together. This is what is governing it. And so understanding all the interesting and unique areas of the mathematics that's involved in this is also crucial. And so, moral of the story here is I started studying neutron stars because I wanted to get as much exposure to all the different areas of physics as I could. I wanted to also get exposure to the extremes of those areas of physics, but what I didn't realize is that I would also get exposure to a wide range of different areas of STEM and also the extremes of STEM. And so if you're interested in STEM, science, technology, engineering, mathematics, neutron stars are a fantastic place. And David Pines, I assume, was talking more so about the physics with regard to neutron stars, but he could not be more correct in saying that neutron stars are superstars, not just because of the super exposure and super wealth of physics, but because of the super exposure and the super wealth of STEM that you would encounter by studying neutron stars. Now, not to mention that there are also a number of super qualities or bits of vocabulary that contain the word super in it. When studying neutron stars, for example, they form in supernovas. We know that they are super dense, also because they're so super dense, and because pulsars spin super fast. We know that they're super smooth. We know that they're super conducting. We know we know that they are super precise with timing, especially with pulsars. But then they can also show super glitches, which is really interesting from that matter. We know that they are, because of how dense they are, they're super small. Okay. We see super high concentrations of neutrons existing outside the nucleus of the atom. I mean, the list could really go on and on. Maybe I'll do like a running list on this after I edit it. I don't know, because I'm sure if I were to actually go through and list out all the different super qualities of neutron stars, plenty of you would probably be really sick of me with regard to that. But I want to thank you all very much for watching. I hope to see you again next time.